Hello my friends, this is Noah and welcome back to the Learn Meta-Analysis channel. In this video, we are going to be going through how to do a multi-level meta-analysis using JASP. We are going to use standardized mean difference effect sizes. Now, one thing that I do want to mention is that we are not going to be using correlated and hierarchical effects. Instead, we're just going to be using hierarchical effects, okay? So that said, let's go ahead and get started. So the first thing that we're going to do is open up JASP. As you can see here, I've already opened it and I told it to open a new data set, which is why it's pretty much blank. But what we will do instead is I'm going to open an existing file. So let me just navigate and go find my existing file now. There will be a link for you in the description of the video. So I'm going to go here and then I'm just going to go to my computer and I'm going to browse. And I need to find this file, which is of course somewhere I do not remember. There we go. Okay, so, oh, that's so annoying. Okay, it opened in a new window. Let me fix that for you real quick. Okay, so here we are in our data set. So as you can see, we have the effect size number as a first column, followed by the study. And one thing that I want you to notice is the effect size number is simply sequentially numbered, 1 through 35, whereas the study is the name of the study that it was extracted from. And here there are things that match. Now, what I mean by that is if we look at this first one, it's Abadia et al. 2019, as is the second. That is because these are two different comparisons that came from the same study. And we're going to use this study column as a clustering variable. And so we want to make sure that these are identical when comparisons came from the exact same study. Now, I do have a bunch of moderator variables in here. I'm not going to go over each one of those because they're kind of meaningless for this example right now. But what I want to focus on instead is our data. So, and when I say data, I mean our outcome data. So I have coded the mean, standard deviation, and sample size of both the experimental groups and the control group here. But I have not calculated the effect sizes yet. So we're going to do that first. Now, I already have the meta-analysis module added to JASP, as you can see. But if you don't have that showing up here, all you got to do is go over to this big plus in the top right, click on it, and then look, you have this meta-analysis module you can just turn on. So to calculate an effect size, we're going to click on meta-analysis, and we're going to click on effect size computation. From here, I have independent groups, I have measurement as quantitative, and I have SMD as my effect size, because that's what I'm going to do. But of course, there's plenty of other options as well. So the mean of control group 1, I'm just going to put my experimental group and I'm just going to plug and chug these numbers in. I'm not going to explain where they all go. Basically, anything group 1 is experimental group. Anything group 2 is our control group. Get these plugged in here. Whoops, I missed one. There we go. All right, control group, and control group. Wonderful. All right, so you can see it computed 35 standardized mean difference effect sizes for us. And I'm just going to minimize this little module. And if I go back to edit my data, you can see that if I scroll over to the right, I now have these new columns, effect size and effect size standard error. So let's go ahead, go back to our analyses and do a meta-analysis. Now, what we're going to do for this multi-level meta-analysis is we are going to click on the multi-level meta-analysis button. So it brings up a little window like this. We are just going to plug and chug some variables here at first. So effect size, we just computed that. Our effect size standard error, we're going to use that. We're going to leave this on REML unless you have a reason to change it. Same thing with fixed effect size of t. Both of these are recommended by the metaphor package, which is what this is using in the background. It's using the metaphor package for R, and these improve our inference. So I'm going to leave predictors empty right now, and I'm going to jump down to clustering. Now, my clustering variable, as I mentioned earlier, was study. So I'm going to click on that. And for study labels, I'm going to put the effect size number for now, just so that it knows it's sequential. And you can see it's got a little complaint here because it says as nominal. It looks like 1, 2, 3, 4, 5. It's just letting us know what it looks like because it says there's 35 levels. That's fine with me because that's why it's numbered sequentially. So let's move down. We're not going to mess with this effect size variance covariance matrix right now. Oh, you know what? I forgot to tell you. I want to turn on the R code so we can actually see what's happening in the background. So to do that, I just go down to advanced and do show metaphor code for R. And now you can see what's happening. So what this is saying is it's saying we're going to do a multivariate meta-analysis. This is our effect size. So YI stands for effect size, compute effect size. Variance, we are going to use our computed standard error squared. And data, we have our data set. The method, we're using REML. Test, we're using T. And our confidence interval is going to be 95%. And then it's saying we're going to use robust variance estimation. And you can see that because it has robust. And we have our clusters labeled as the study, which is what we want. So that said, let me get this back out of the way here. Okay, so here we are. Next, we need to actually set up our 3-level structure because we have not done that yet, right? So what we are going to do is we are going to go ahead and go into this random effects model component. So you can see it's already set up as nested. So at level 1, I mentioned earlier that we have effect sizes nested within studies. So my higher level of those two is the study, and then the effect size number is nested within it. You see, so level 1, study, level 2, effect size number. So what do we see? Over here on the right, you can now see we have a little bit more information, right? So what are we looking at? Let's take a look at what we see now. We see that our overall heterogeneity is statistically significant, right? We can see our Q-test here is statistically significant. Our pooled effect, on the other hand, is not. So we see we have a negative t-value, but importantly, our p-value is not less than 0.05. So we do have an overall meta-analytic estimate of negative 0.38, but it is not a statistically significant effect. So what do we do now? Next, we want to look at more of the information about the model itself, okay? So what do we see? First of all, we can see that we structured this appropriately because we have 12 levels. This is our for our first level, so that's the number of individual studies, because we had 35 effect sizes and they came from 12 studies. So we can see here that our structure is good. And the other thing is when we look at this R code, we can also confirm that the structure is good because we have studies and their effect size numbers nested within it. So when we're looking at this, we know that we now have a non-significant overall effect. So basically, our meta-analysis found there's no statistically significant effect of whatever this intervention was on control group. I don't remember. Okay, so next, I would want to look at the diagnostics. So I would open up this case-wise diagnostics, and you can see that's opening up a table where it has a standardized residual, the Cook's distance, and the hat value. Now, I will say one thing that I like more about simple meta-analysis software than JASP for this is in simple meta-analysis, I built in another column that flags these things automatically if they are something that are influential for your data set. So that said, I do not remember the actual values here of what we should be looking for, but I will include a link in the description to some information that talks about that. But I will say, even with case-wise diagnostics, at least at the time that I am recording this here in mid-2025, I don't know that there are well-defined values for what is considered an influential study in a 3-level meta-analysis as opposed to a 2-level meta-analysis or a conventional meta-analysis. If you guys know more about that than I do, please include a link to a paper. I would love to read it if there is a paper somewhere out there about that. So that said, I will provide a link to you guys so you can go through and see which of these are significant or not significant. That's just one thing as I was going through this earlier today that I was like, you know, that's one feature I'm really glad I built into simple meta-analysis was this automatic flag, because I quite frankly find it much faster than looking at each one of these things individually. But for the sake of time, we are going to pretend that all of these are not influential in any way, or if they are, there wasn't some issue with the primary study. We're going to leave those all in there and we are going to continue. So what do we want to do next? Well, next we might decide that we want, let's see, a moderator analysis. You guys want to do a moderator analysis? Yeah, let's do a moderator analysis. So let's go up here and we're going to go to predictors. So the predictor that I'm going to use is, let's say, the control condition. That sounds fun. So I'm going to add that into my model. And then I'm going to minimize this random effects and I'm going to open up the model, and you can see it now includes the control condition and saying it's including the intercept. The thing that I want to highlight here, because down here in the results, you can now see that when we are looking at the moderators, you see we have this new line here, mods control C. And so this is telling us that we do in fact have our moderator in the actual data set. So when I scroll up to the top, you can see the overall meta-analytic tests, we have a moderation test now. And we need to be careful with this, okay? We need to be very careful because watch what happens when I click this include intercept button. That test still is there, isn't it? But the number changed. Look at this p-value. So you see now it's 5.25. And when that's back on, including the intercept, it's now 0.60. These are very different things, right? These are very, very, very different things. And when we look down here at our meta-regression summary, you can see the effect size coefficients. They're listed here. And so what's interesting about this, guys? What's interesting here is we have the intercept when the intercept is on. Now watch, when I turn that intercept off, what happens? Now, instead, we have all three groups listed, and our estimates change a little bit just because all three groups are listed instead of being listed as an intercept. You can do some math to make them be the same, but long story short, here's what I want to tell you. This is the takeaway message right here for moderation. When you include the intercept, your test of moderation is testing if there's significant differences between groups or between levels of this moderator. So it's answering the question of, is there a significant difference between virtual reality as compared to traditional video? In this case, when we look at our test of moderation, you can see the answer is no. There is not a significant difference between these two. Okay, so why would we want to exclude the intercept then? The reason we would exclude the intercept is because in some fields, like my own, we would often use this table here that lists all three values rather than including the intercept value when we are doing a categorical moderator analysis like this. Now, you may be wondering, when there is no intercept, what is this test of moderation testing? And the answer is testing if this is statistically different than 0. So very different test that's happening here. And we want to make sure that we are interpreting the correct one. So I'm just going to go ahead and click this on, and I'm going to actually remove the predictor from the model to show you guys the next thing. So I'm going to minimize some modules here just to get them out of the way. And I'm going to go to forest plot because that's another thing that you may want to make. Now, first, I'm going to click on study information, and you can see it gives me this really basic forest plot, which is great, but it's also kind of annoying. So I'm going to click on study and move that over. And what that's going to do is it's going to give me my study names. Now we're looking better, right? Now it's much less annoying because it actually has some data, it has some labels, it's useful. So the study, we can just call this, oh boy, I have way too many things in front of my keyboard right now, but we can call this study, whoops. And when we add that text in to this little box, you can see it is going to, I need to click off of it. There we go. It's going to include that there. So now we have all sorts of different options of things that we can turn on and off. I'm not going to really do this because honestly, I feel like you guys are smart folks. You can figure out what happened. Like we click study weights. What's it going to do? It's going to put study weights also on our chart, just like that. So helpful things depending upon your field. You know, the norms are a little bit different. Now the order, this is one that I think is a little bit interesting because in my field, we would typically present it like this. Most standardly, we're going to present it like this, where all the comparisons from the same study are all listed together. But I can definitely see situations where this may not tell the story as well as you want. And perhaps you want to look at it by the size of the effect size. And so what I did is I chose the order. We're going to go by the effect size. And then I chose ascending. So it starts down here and it gets bigger as it goes. So depending upon your field and what the norms are and what you want to tell, like how you want to tell the story and how you want to present your data, there's a number of different options that you can use here. So I'm just going to turn this back to no choice because that's more typically what I would see in my field. So the last thing that I want to point out here is this idea of aggregate, right? So when we hover over this, we can see that it can take the study level information by variable. So let's try this out. Let's try aggregating by study and see what that does. Oh, now that tells us something cool, doesn't it, guys? Look at this. So what this did is it combined all those effect sizes and it put them instead by study. And so that now we're looking at it by study instead of by comparison. Now, one thing I do want to try is changing this to bubbles. Oh, fun. Okay. I hadn't tried that before. I just really wanted to see what it did. I prefer the box plot. Personally, I like the box plots more. But the other thing is you can really change this and have it aggregated by whatever you wanted. So we were looking at the control condition earlier. So let's go ahead and try that. And you can see now it is clustering by the control condition and it's telling us which studies are here. Now, what if you didn't want these studies to be what's listed? You instead want to know like by which control condition. Then what we can do is go up here, move this back over. Oh, I'm sorry. I pushed the wrong button. So we're going to click on study, move that over, and then I'm going to choose Control C and put that as my selected variable. And look, now it's labeled much more clearly, right? So this is actually really informative for us, isn't it? So when we're looking at this, we can see virtual reality. We have huge variance here, like a huge range, right? Look at this. Look how ridiculous this is. Whereas with traditional video, it is a much, much tighter distribution. So really informative things that we can do with the forest plot. Tons of options here that can help us visualize our data and help us tell our story pretty clearly. The other things that we can do, I'm just going to scroll down. You know what? Let me do this first. Let me get our forest plot back to a standard forest plot just for the sake of conversation. And so it is more typical of what you would see. So here we are here. We have our more standard forest plot, so to speak. I'm going to just put this selected study variable back on so that we add in the names. Now this is what we would normally see. This is probably what you guys are used to. I'm going to just re-add the term study here so that it is labeled. Click off of it so it's going to appear. Okay, so this is like a standard, quote unquote, standard forest plot. So let's go down here to model information. Now, the cool thing about the model information is it printed this for us on here. We have our Q value, statistically significant. We have our effect size value, not statistically significant. And we can see our overall effect size down here at the bottom. Okay, so tons of options. I'm not going to go through the rest of these options. And oh, last but not least, you guys are probably wondering about publication bias, aren't you? Well, let me tell you this. As of now, in mid-2025, I do not know of any reliable methods for looking at publication bias across all meta-analyses. Like, I can't just say for a multi-level meta-analysis, you should use this test. Well, for now, I think one of the best things that we can do is look at a forest plot. So why don't we go look at a forest plot of our effect sizes, okay? Oh, I'm sorry, I said forest plot. I actually meant funnel plot. So let's go take a look at a funnel plot of our effect sizes. So I'm gonna go up here to meta-analysis, and I'm gonna click on funnel plot. Now, something that I want to mention, this is another difference between, well, let me create it and then I'll tell you. Sorry, I get a little ahead of myself. So let me scroll down. I'm going to move my effect size over. I'm going to move my standard error over, and I'm going to add in my study labels. Oh, actually, I'm not going to use study labels. That makes it too clustered, for like too messy for me. It's hard to read. Okay, so the next thing that I want to do is, personally, I like to move to the funnel under H1. So if you look, it's the funnel under the null hypothesis. So it's centered at 0, right? So I'm going to turn on the funnel under H1 so you can see what happens when we do that. And now I'm going to turn off funnel under 0. So when it's under H1, this is looking at our overall effect size. So you can see how the funnel plot is in relation to the overall effect size found in the meta-analysis. So we found like a negative 0.38, but it seems to me that like there's a little bit of an issue with, oh, that's why there's an issue with scaling. It's because this guy's all the way out here at like a -7 or a -8, right? So that's why it's like way off to the side. So it's a little bit hard to read. But basically what we would be doing here is looking to see if we have some sort of symmetry between the effect sizes on each side of the overall effect. In this case, it is not symmetrical, right? I don't think this is symmetrical really at all. Everything's stacked way up on the right. There isn't much over here on the left. So in this case, it's probably safe to say that we have some significant, well, we could check the case-wise diagnostics, right? That's what we should have checked before. I would assume that we would find under those case-wise diagnostics that some of these are significantly influencing things, but maybe they aren't. We would need to look at those case-wise diagnostics. And like I said, I just gave you guys the link to go find those numbers because it wasn't flagged and I didn't feel like doing it right now to go look that up. So anyway, what we can see is this is my conclusions that I would have here is this is not symmetrical. So we have some sort of publication bias happening. Now, the next thing I want to point out is there are these publication bias tests down here. Fail-safe ends, trim and fills, asymmetry tests, things like that. I would not be using these right now with a multi-level meta-analysis like this. I will say that if I remember correctly, there is a variant of Egger's test that works in some situations, but I have not read the paper recently enough to remember the details on that. So like I said, there's a link in the description so that if you're doing one of these multi-level meta-analyses, you can go find out how to do that. I do not know if it's actually implemented in JASP or if you would have to do it in R. So let's summarize what we've done, okay? We have done a multi-level meta-analysis, in this case, a 3-level meta-analysis. We used hierarchical effects. Now, this is an important distinction, okay? I'm going to include another link in the description that talks about the difference between hierarchical effects, correlated effects, and correlated and hierarchical effects all in the same model, because there's different assumptions here, right? There's different assumptions that go along with each one. So this was a hierarchical effects model, and we used robust variance estimation. So the results might be a little bit different than if you had done correlated and hierarchical effects. And so if you want to do correlated and hierarchical effects, I have a video on how to do that in R on the YouTube channel. If I remember, I'll put a link to that in the description as well. So if you're seeing differences in the scores or the overall effect sizes between the model that I had posted on how to do this in R. And what we got here, it's because that one is using correlated and hierarchical effects, and this is not using correlated and hierarchical effects. It is just using the hierarchical structure. So that said, we did our analysis, our overall meta-analysis. We built a forest plot. We looked at the heterogeneity in our analysis. We ran a categorical moderator analysis, and we did the best we could looking at publication bias, and we also talked about how to look at influence. So that's pretty much everything I wanted to say. JASP is a very powerful program. It keeps getting better and better with each iteration, in my personal opinion, in regards to doing meta-analysis. It's very simple to do a multi-level meta-analysis here. The question that comes to mind for me is, would I use this as opposed to my simple meta-analysis software? The answer to that, in my opinion, has to do with what you are looking to accomplish. For me and the types of analyses that I do, I mean, I built simple meta-analysis, so I built it to do the types of analyses that I do. So that's very fast and easy for me. But JASP is way more flexible in what you can do than my software is. And that is because JASP is built for many people, as compared to simple meta-analysis was built for essentially very few use cases. So I think it really depends on what you are looking to do. And yeah, I'll leave it at that. So I hope this video has been helpful for you guys. If you have any questions, please feel free to leave them in the comments. Otherwise, please like and subscribe to help support the channel. And thank you guys. I hope you have an absolutely wonderful weekend.